Hello, I'm hoping you all can hear me. Could someone let me know if you can? Okay. And if like normal, I can't hear you, well, I guess you can always type something in the chat, but I'm going to be positive and assume I could hear you just fine if you were to unmute and have a question. Okay. Uh, yeah, my volume is loud enough. Okay, normal thing. Let's just do it. And I want to start with sharing a screen and then some announcements. And I think we'll get down the right path, the normal thing that we do today. Okay, geez, it's week 5 and it's Tuesday of week 5, which means we should probably make sure we're all on the same page. One thing is, there's this final exam. You should show up for it. And unless I already know and have agreed with you about, oh, you were taking the test at DRC or something else, yeah, I'll see you in person on Thursday, July 23. Just 2 days from now, shoot, 48 hours from now, I'll be handing out tests, or I'll just completed handing out tests. It's a 2 hour test. Actually, it's an hour and a half test, but you have 2 hours to do it. In the Baker Building, room 113, that's ground floor. You enter from the west side, or you enter from any of the other things, and then just go down the stairs or the elevator, and it's fine. In advance of the exam, on the day of the exam, there will be office hours opportunities. So show up then a little bit early if you want to. If you've got questions, let's chat about those things before too late. Getting into this week's content. The first thing I want to do is just note that 2 years ago, before a collection of students took their final exam, with the same exact sample exam content as you guys have, they had a collection of questions. And so drawing your attention to that would be good because you could watch them ask questions and then you could also follow along, play the home game. And then also, I guess, if you have additional questions, there are opportunities tomorrow in office hours. And it's a Monday, Wednesday, tomorrow. So that'd be office hours at 1:10 to 1:35, and then 3:25 to 3:50. So between the two classes is tomorrow's office hours, Wednesday's office hours. So come by and ask questions about the sample exam, then that's good. And then if I'm looking through what has to happen this week, we're already a third of the way done. At the end of today, we should be 2/3 of the way done. We're gonna dot some I's, cross some T's about analysis of variance. Okay. We learned last time the basics of ANOVA. Okay. Today we're going to tackle two questions. One of those questions is, what if you say, oh, look, there's a difference between the means? Mm-hmm. Oh, you might naturally want to say which means are different and in what way are those means different from each other. We'll tackle that first. And then we'll second off tackle the question of, well, what if you have more than one explanatory variable? What if there's two factors that separately could impact the results? How would that change things up? We're going to talk about a two-way analysis of variance in the context of two-way analysis of variance in the context of shoot, I just saw something I need to change. Two-way analysis variance in the context of a balanced design. In other words, the same number of data points for each exact treatment combination. And what I need to change up is to provide that link to you. So that will be done within 3 minutes after class ends today. Okay. Homework problems that tie to what we're doing is out of a little bit more in chapter 9 and some in chapter 10. And you're wondering about Wednesday. Wednesday is, oh, remember that regression thing that we did? Well, if there are a collection of assumptions that we could make reasonably that I'll call the simple linear regression model, we could do more than just fit a trend line. We can actually test hypotheses about the slope and even come up with a way of estimating the typical value of y for any given x. And so there's going to be material tomorrow as well that is going to be related to the final exam. So that's a collection of things I thought I should bring to your attention. I don't know if you have any questions about those administrative matters. If you do, please unmute and let me know now. Okay, so let's move.
Sorry, I apologize if you already noted this. Is there a mock exam or practice exam?
Oh yeah, great question. I believe there is a sample exam, and let's look and see where that is. Because I think I looked my way into it yesterday, but that might have been for the other class. So summer 2022, the sample final exam questions. Yeah, those are the ones that are video from 2 years ago covers. And so you just click your way into where it says exams, okay? And you should have then indeed our and yes, I should have put our exam two questions and then answers online as well. So I need to do two changes, but that's a little bit lower priority than making the lab live. So thank you, Manuel. You want to follow up on that?
No, that's it. Thank you.
Anyone else for anything administrative? How about anyone for anything related to analysis of variance, what we talked about in class yesterday? Okay, so what I want to do is to start down the new content for the day. And it's all the way over here. Good. So new content. Um, what if at least one of the means is different from the others? I guess our ANOVA context is the null hypothesis, and maybe. Okay, come on. The null hypothesis in an analysis of variance. Okay, so let's, okay, undo that. And then the null hypothesis. Okay, so I seem to have a goofy setup right now with the Apple Pencil, and now we're connected differently and better. Okay, so um, okay. The null hypothesis in an analysis of variance is mu1 equals mu2 equals mu3 equals all the way up to mu k. Okay. And if you reject that null hypothesis, you sort of say at least one of the means is different from the others. Which one is it that's different? Okay. The solution that we have to try and tackle that problem is to say, well, let's just do a whole bunch of, I won't say t-tests, but t-based confidence intervals. Because if I could tell you, okay, for mu A minus mu B, is that less than zero? Okay, it's either less than zero or it's equal to zero or it's greater than zero. And for each of these three cases, okay, if mu A minus mu B is less than zero, you know mu B is bigger than mu A. And if mu A and mu B are equal to each other, I guess mu A minus mu B would be zero. Or if mu A minus mu B is greater than zero, you know which mean is greater. So a 95% confidence interval for mu A minus mu B sort of answers all the questions. And the nice thing is the confidence interval will either include zero, or it will be strictly negative, or it will be strictly positive. And if I tell you for every possible combination of A and B, every possible group mean compared to every other group mean, which is negative, which is positive, I can sort of tell you, yes, this is how they line up, shortest to tallest. Let's look at an example of that. And I've got fun data set, discrimination. This is a study from Ohio State where a collection of business majors who wanted to be HR people, and so they're like in human resources area of emphasis. So they should be good at evaluating whether people are good for the job. Okay. They were given a videotaped interview to watch. Okay. More about that in a second. And when they watched the video, okay, the video either showed someone as having no apparent handicap, maybe showed an amputation, maybe showed the person with crutches, okay, or perhaps their a hearing area was showed in the video, or the person rolled into the interview with a wheelchair. So there's five different videotaped treatments, and you sort of think, how well qualified is the person for the job? A low score means not very well qualified. A high score means that's a person who seems to be very qualified for the position, according to the position description. So these folks watch these videotapes and just rate the candidates and their qualifications. What was not known to the people watching the videotaped job interview is that it was the same script, the same two actors, and everything was the same except for the appearance of no apparent handicap or an amputation or crutches or hearing loss or a wheelchair. Literally, the same two actors were doing the same thing. And if you didn't see the videotape and see literally the hearing aid in the person's ear, you would have read the same. You would have viewed the interview the same way. You would have said, aha, these are equal people. The only difference was the appearance of a handicap. And so these folks were being evaluated on a job where this particular set of handicap possible options, amputee or crutches, etc., has no effect on the ability to do the job properly. And so you're watching these five videotapes or one of the five videotapes, and you're giving a score if you're one of these HR students. And the natural question comes to mind, are the means the same, or is at least one of the means different? Under analyze fit y by x, we know from the past across these different handicap groups, maybe the score is different on average, maybe not. And it looks here as though maybe the crutch group has a slightly higher mean than the others. Maybe the hearing loss group has a slightly lower mean than the others. Is it statistically significant? Under means and ANOVA, we turn it on, we see the p-value says, yes, there is a statistically noticeable relationship. At least one of the handicap groups has a different average score than do the others. And it seems as though we do have the means given to us and their confidence intervals shown. Please ignore those. Those are confidence intervals for individual means. What we want to do is talk about confidence intervals for one minus the other, mu A minus mu B, for every A-B combination. The problem with confidence intervals, though, is if you give me a collection of 10 95% confidence intervals. So there's amputee compared to crutch, amputee compared to hearing loss, amputee compared to none, amputee compared to wheelchair, crutch compared to hearing, crutch, none, crutch, wheelchair, hearing, none, hearing, wheelchair, none, wheelchair. 10 separate comparisons, 10 separate confidence intervals. And if each of them is 95% certain to capture the truth, each of those has a 5% rate of error, 5% likelihood that they will not capture the true difference of population means. And if I've got 10 procedures, each of which is 5% of the time going to make an error, the overall rate of error is going to be pushed upwards from 5% overall across the collection to as much as 50% overall across the collection. I don't love that. In fact, I sort of much hate that. So the idea that we have is to do a little bit of probability calculations. And if you read through our book and you look for Bonferroni, Bonferroni, it will walk you through the logic of the idea. We're going to suggest something called the Tukey-Kramer procedure. The upshot is If I increase the level of confidence from 95% to 99%, you get maybe only 1% rate of type 1 error, and across 10 procedures, each of which has a 1% rate of error, the overall error rate will be a lot lower than earlier when each of the procedures was at a 95% level of confidence. Maybe if we boost the level of confidence in each of the 10 individual procedures enough, we will end up with 95% confidence overall. So let me show you how you could do that. With our one-way ANOVA, okay, we did our analysis and said at least one of these means is different from the others. We said, yeah, there we go. Under here, options, compare means. Let's compare the means to each other. And I did suggest using all pairs, comma, Tukey. HSD stands for honest significant difference. The notion is we're doing multiple procedures post hoc. Which of them is overall a real difference? If I turn on that, we see JMP already does a whole bunch of things. I don't love the circle thing. I'm going to ignore the circle thing. What I do want to go down here is note that in my overall, maybe I'll raise this up so we can see more easily. Overall, now we have our collection of results. There's this number here called Q star that goes with 95% confidence or a 5% rate of error overall. I'm going to ignore this for now. We could talk in office hours if you want it. I'm going to ignore this connecting letters report and jump right down into if I use, instead of T star in the confidence interval, if I use Q star 2.8 standard errors up and down, then a collection of 2.8 times that standard error for the difference added and subtracted to a given difference of means will give me a confidence interval lower and upper end. And if the lower upper end is negative and the upper end is positive, we're seeing there's not a noticeable difference. If zero is inside the confidence interval, zero is a plausible value for mu A minus mu B. And so I'm looking for only situations where the upper is positive and the lower is positive. We sort the differences from largest to smallest differences. We put them in an order here off to the left that corresponds to larger minus smaller. And the crutch mean minus the hearing loss mean is like about 1.8. With our standard error, we give a confidence interval that we're 95% sure that mu crutch minus mu hearing loss is like 0.14 up to 3.6. It's statistically noticeable, the difference, that the crutch group is higher than the hearing loss group. And it does seem as though there's a lot of other differences that we could look at. And in all of those cases, we see that the lower level is negative, the upper is positive. I'd say I'm not spotting any differences other than the crutch group and the hearing loss group are apparently different from each other. JMP produces what they call a connecting letters report, and that connecting letters report essentially puts our groups into categories that correspond to I can't see a difference between. Literally, group A says none of these groups, okay, collection A, okay, a crutches, wheelchair, none, and amputee. I can't spot a difference between any of them and any of the others. In this crutch, wheelchair, none, amputee group, I'm saying I don't spot a difference between any of them. Similarly, for group B, it's a wheelchair, none, amputee, and hearing. And I'm saying across these 1, 2, 3, 4 different treatments, I don't see a difference in any of those means either. How could we reproduce that connecting letters report ourselves? Inside this inside this ordered differences report, plus I guess the means, we have the ability to do everything we need. So what I want to do is reproduce that right now for I'm going to put the order lowest up to highest, and let's make that over here off to the left so it's small enough that I can see. Okay, so which is the lowest mean in the amputee crutch hearing loss wheelchair none? Oh, the hearing loss group has the lowest overall mean. So I'm going to put H off to the left. Hearing loss has the lowest mean at 4.05. Then it's amputee at the 4.23. No apparent handicap. N in that group. Well, maybe I'll erase that so we can see exactly what the N value is. 4.9. And then wheelchair, clocking in at 5.3. And W for wheelchair. And then finally the crutch group with highest. I mean, you list them in order lowest to highest, to be honest. We had them highest to lowest. The procedure we're going to suggest will still work, but lowest to highest, as you go from the left to the right, the numbers should increase. Okay. And what I'm spotting now, once I put them in order lowest to highest, is within my ordered differences report, I could compare group H with group A. And is there a noticeable difference between the hearing loss and the amputee group? Let's go down here and look. Hearing loss and amputee is at the very bottom. The hearing loss and amputee group, there is a 0 inside the confidence interval. Hearing loss and amputee could have the same population mean. I need to underline these together. They're literally in the same group. I can't tell the difference between them. Underline them together. Okay, so I haven't compared hearing loss with no apparent handicap, H, compared to N. Let's look for none and hearing loss. Again, negative and positive. I need to continue my underlining from H all the way through at least N. Let's compare hearing loss with the wheelchair group. A wheelchair and hearing loss. Wheelchair hearing is right here. Wheelchair and hearing. I see a negative and a positive, and I need to continue the underlining from H all the way through the W. So what about hearing loss compared to crutch group? Okay. Is there a noticeable difference, hearing and crutch? Oh, look, they both are of the same sign. 0 is not inside that confidence interval. So hearing loss, the first group that began the underlining, is clearly different from the crutch group was not included. I cannot continue that underlining. I can't. Sorry. Oh well. Whew. So my first underlining is finished. Now I have to compare the first group that did not begin the previous underlining to the first group that wasn't included in it, amputee and crutch. Let's see if the amputee and the crutch group are noticeably different. Crutch and amputee. Negative and positive, there is not a difference. And so the amputee group, which did not begin the first underlining, has to begin the second one because it is not noticeably different from the crutch group. And this is what gives us our ordered or connecting letters report. Group crutch, wheelchair, not an amputee. Crutch, wheelchair, not an amputee. That's this second line. Group B is the hearing, amputee, non-wheelchair. Hearing, amputee, non-wheelchair. So how would we interpret this overall figure? I would say which group is compared to which other group not commonly underlined with one underlining. The hearing loss and the crutch. So I'd say, look, there is a noticeable difference between the hearing loss group and the crutch group. And then I'm done. Because every other possible comparison of any one group with any other group, they're in a common underlining. Now, let me caution you about one thing. Don't ever use the word similar here. Don't say hearing loss is similar to no apparent handicap. No, 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 no. Just say there's not a noticeable difference between hearing loss and no apparent handicap. We can't spot a difference. That doesn't mean that there is a similarity. Okay. I like to view this as sort of like that social function where you should not invite both Hank and Charles. Hank and the Charles, each of them get along with Andrew, and what's an N name? Norbert. I know a Norbert, and W for William. Okay, so Hank, fine to go with these other three. Charles, fine to go with the other three. But if you invite Hank and Charles to the exact same function, there is a noticeable, clear difference between them. You should not have done that. We've all been to those parties and we all know what happens. So tell me where there is a noticeable difference. Tell me every possible notable difference. And then say, beyond that, we don't see any differences at all. Any questions about the post hoc, the Tukey post hoc procedure? Okay, so what I want to then do is move on and talk about okay, the next topic for the day. And that is rather than comparing the means, it's sometimes a bit more convenient to speak about effects. What is the effect on the mean of being in the group you're in? I'm going to just start with an algebraic identity. The mean of group I is equal to some reference number that I'll call mu plus alpha I. Alpha I is the effect of being in group I, the effect on the mean. I guess if I wanted to rearrange my friends algebraically, alpha I is mu I minus some reference value mu. So the effect, okay, alpha is how different is this group on average from the reference. Now notice that we haven't defined the reference yet. What is a natural reference? What is mu? Well, I'm going to give you two different ways of thinking about it. One is mu is, if you will, the average of all the mu, I guess the average of the mu hats, and each mu hat I is just the X bar for group I. So I'm going to average the individual group means. Okay. So mu hat is an average of all the group means. There you go. That's if you want to compare to the average across all the groups. You could also have mu hat is equal to 1 mu hat for group I, for maybe group, let's call group 1, okay? X bar for group 1. That is one way of thinking. There is a reference group, a control group. We're going to say, let's compare every group to that group. Or I could say, you know what? Mu hat should be the average across a collection of group means. The software chooses this style, the first style. And there's nothing wrong with either of them. But I'm just going to say if we define the average of all the group averages as my number mu hat, then alpha hat, my estimated effect of being in group I, is just equal to mu hat or mu I hat minus mu hat. Oh, that's X bar for group I minus the mean of the X bars. That's, again, we're going to call it mu hat. Now, here, a quick aside comment. It turns out if you have the same number of data points, yeah, for each of the different groups, then this could also be written as X bar for group I minus X bar bar. But in general, we like to avoid assuming that you have the same number of data points per group. But if you did, it's X bar for the group minus the grand mean. It tells you the effect of being in this group on the mean. Okay. So that's a pretty straightforward, easy thing to do. The benefit of stating things in terms of the effects is you could then say, aha, there is no effect of being in this particular treatment on the response. Let me state my null hypotheses two different ways. My null hypothesis, the way I would have phrased it yesterday. No, let's remove that. Okay, null hypothesis from yesterday is that mu1 equals mu2 equals all the way up to mu k Now today I'm going to say, no, 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 no. Today I'm going to say, uh, alpha 1 equals alpha 2 equals all the way up to alpha k equals 0. Two separate identical ways of saying the same thing. My null hypothesis is there is no effect, or the effect of which group you're in on the mean is no effect. It doesn't change the mean to be in the group you're in. So let me show you how you could pull that off with the data set that we just looked at, my discrimination against the handicap data. And I'm going to show you a slightly different approach to our earlier we said under analyze fit y by x. I'm going to say for the convenience of understanding, I'm going to use this thing called analyze fit model. Actually, you could do either thing, either approach, but for my sake, pedagogically, right now, I'm going to use analyze fit model. And I still say, does the score depend on the handicap? That's a question. I click run, and I get a collection of output, not all of which I want to look at. And let's focus on the things that we care most about. I'm spotting here the same ANOVA, the same p-value as before, but I want to look at this thing called parameter estimates. Here in this intercept is like the average score given across all the groups. And the effect of the amputation in the videotape is to reduce the score by 0.5. The effect of crutches is to increase the score by 0.99. You're sort of thinking there's only 1, 2, 3, 4 effects. What's with the fifth? GMP is really just smart. It says if I tell you the first 1, 2, 3, 4 estimated effects, and if you know the sum of the five is 0, the sum of the first four, change then the sign will give you the fifth. But if you don't even like to add and then subtract from 0, under estimates, you can literally turn on what are called the expanded amputee crutch hearing and none effects. You also get the wheelchair effect, but the sum of these 1, 2, 3, 4, 5 alpha hats is exactly 0. So we basically could say, let's compare the groups and let's see how each group is different from the mean. Here are my estimated alpha hats. If you were to tell me, and let's go with fit y by x, this is the same one we had before. If you're going to tell me the average score for each of the handicap groups, boom. And if you turn on the means and standard deviations, if you just tell me X bar for each of the 1, 2, 3, 4, 5 groups, I could literally average those 1, 2, 3, 4, 5 X bars, and I'm going to get the grand mean. Okay. And I could compare each group mean to that X bar. And the claim is the software has already done that for you. Here's your X bar, the grand mean, the average across all 5 group means. And then how different each group mean is from the average across all 5. The lab will walk you through doing that. Okay. But I told you that story to tell you this one. Sometimes there's more than one explanatory variable that might have an impact on the response. I might believe that the individual Y score is some average value plus an alpha hat based on what treatment you're getting in one sense. Plus, then I'm going to go with a gamma J, okay, for another treatment effect. Plus, I'm going to go with epsilon, an error around the trend line, if you will. Okay. There could be more than one effect. Basically, you're thinking there is a treatment effect. And there's a treatment to effect. You could have two separate impacts on the response. If you've got multiple factors that could separately impact the response, think conceptually. There is an average response, but that each of the effects could have its own separate impact. A data set that I like to trot out for this purpose. Let's see if I can find it. It is, I think I've called it Bricks September 30th. Oh, September 28th. Bricks 3, September 28th. Okay. So in the context of a model like this, you'd sort of say, okay, what we're going to do is measure the average specific gravity in a bunch of grape juice based on, if you will, the individual below ground portion of the plant, the rootstock, if you will, and the above ground portion of the plant. It's called clone or the clonal variant, or sometimes called the scion. This is clearly an ag experiment. And you can spot that there's one, two, three, four different above ground portions: the 23, the 115, 667, 771. And there's five different rootstocks: a Schwartzman, Rapidia Gloria, or R Gloria 3309, 110R, 101-14. These are just literally genetically identical plants that you could buy out of a catalog. And you get someone delivers you a little thing labeled Scion 23. And so you know it's a clonal, it's an exact clonal match to all the other Scion 23s that you got, and you got four of them. Okay. I'm sorry, you got five of them, and you got a collection of four things labeled R Gloria or Rapidia Gloria. And what we're going to take is the above ground portion and you graft it onto the below ground portion. And if you need to look up grafting, GRAFT, okay. If you look up grafting in Wikipedia, it will tell you, oh, yeah, here's how you deal with fruit. You get a below ground portion, something called the roots, and then you add the top part of the plant to it. And ultimately, you produce grapes that give you sugar. And we measure the specific gravity. So if I was going to look at this data graphically with Graph Builder, to try and do it over here below the level of where we are looking here. The Brix 3 maybe depends on, well, shoot, what clonal variant it is across these different clones. Does it look as though maybe one of the clones, like 771, has a higher specific gravity than another one, like 30 or 23? Maybe. What about rootstock? Well, maybe if I show you the rootstocks in different colors, you're thinking the purple might be different than the brown, might be different from the blue. Okay. Different rootstocks may have different typical sugar contents. So there's the clonal effect, and then there's the rootstock effect on sugar content. There's the average sugar content, plus the effect of what clonal variant it is on the sugar content, and then the rootstock impact on the sugar content. How would I fit such a model as that? Not too bad, really, to be honest. We just did it. Darn it. Under analyze, fit model is the way we're going to go. If you got more than one factor, you use fit model. Why? Sugar content depends on what? It depends on the clone, which clone it is, and maybe it depends on the rootstock. Okay, I click run. And there's a lot of output that naturally appears. Let me try and show you all of it. And maybe, darn it. Okay, so overall, across both clone and rootstock, does at least one of the variables matter? Your p-value says seems to be at least one of them matters. If you want to tackle a question about does the clone matter, you'd say p-value small. The answer seems to be yes. Okay. Our lab will talk about the sums of squares due to the clone impact. Rootstock, does that seem to matter? And p-value says, I don't really see it as mattering. If you want to calculate the alpha hats, the estimated effect of each of the different clonal variants, well, the software will do it for you. Okay. The lab also walks you through a way of doing that. And you're noticing 1, 2, 3 clones, but I said there were 4. Like before, if under estimates, you turn on the expanded estimates, it gives you all 1, 2, 3, 4 clonal estimated effects and all 1, 2, 3, 4, 5 estimated rootstock effects. And it does seem as though the clonal variant is sometimes negative, and noticeably so in at least those two cases, and sometimes it's positive and noticeably so. It does seem as though we could say across the clones One of them is different on average than the other. Across the rootstocks, I don't see any of these as being noticeably differing from zero. My estimated test across all 1, 2, 3, 4, 5 rootstocks says I don't see a difference here. So if you got two factors, no problem. We can handle that. If you got three factors, probably we can handle that. In a well-designed experiment, you basically have the same number of data points for each treatment combination, and you're home free. Here, do we have that? For each of the 1, 2, 3, 4, 5 rootstocks, we've got exactly 4 occurrences of the rootstock, one for each of the clones. For the 110R, we see the 23, 115, 667, 771. For the 3309, I'm sorry, the 3309, again, the exact same 1, 2, 3, 4 treatments for clone. And so we have 20 treatment combinations, 5 rootstocks, 4 clonal variants. 20 is the product of those. We got 20 data points, one for each of those, one replication for each of those treatment combinations. And yet it still works. We can estimate those treatment effects for each of the 2 separate factors. Do any of you have questions about this penultimate topic? Okay. What I need to do is to get the
Uh,
lab on. Oh, yeah, please, question.
what would be the difference between this and a multilinear model?
Great question. We're not talking about multiple regression this term. But as you noted, there is a similarity to regression. Look, if I just had a beta zero and then a slope and then another slope times another x, it looks similar. And it turns out that algebraically, if your x variables, John, are always zeros or ones, depending on which treatment group you're in, you could actually reconstruct this as a multiple regression, but I don't want to go there. I'm just saying there is an algebraic relationship. The same matrix algebra would be used to solve both models. We just choose to present this here as categorical factor, not a linear trend. So I completely ducked the question, John, but I tried to say you're spotting something that I'm glad you spotted, and in a different course down the road, we are less evasive at the answer. Does that get towards what you wanted?
Yeah, so would a layman's description be that it's a multilinear plot, but they're all Boolean values?
Sure, we'll go with that.
Okay.
But that exactly what you said was perfect, except for that is not corresponding to the sum to zero nature of the alpha hats. The way you phrased it, the alpha hats don't necessarily sum to zero across the 4 different clonal variants. Yeah. But it's algebraically the equivalent of what JMP does. Yeah.
So each of the alpha hats could be like, this alpha hat is this percentage of the variance, or is that oversimplifying?
That is something that is exactly dead on right. Each of the alpha hats can explain some percentage of the variability in sugar content, but it's really a collection of them that we treat as a whole. Like across all the clones, overall, there is the sum of squares is like 35, like we talked about yesterday. That's like if I take the standard deviation of y and multiply it approximately by the number of data points, and then standard deviation of y squared, then multiply by the number of data points. That's the sum of squared y. The sum of squares that can be attributed to clone is well over half. So R squared that corresponds to clone itself is over 50%. But R squared attached to rootstock is maybe 10% of the total. You're currently unmuted.
Oh,
I thought
yes.
you were maybe going to say a thing, but
Yeah, I wasn't sure if you were done.
oh, sure, sure.
So it's each of those represents a percentage of the data, of a percentage of the variance, but how does it sum to one? Because aren't you usually not able to get 100% of the variance?
Exactly. Okay, so let's look at this thing called the analysis of variance overall. Overall, there's a variability in some way of measuring it of 35, yeah? What we're able to explain with our model is like 26.8 of that. Of that, clone does about 23.3, and then rootstock does the other 3.5 of the overall 26.8 that we can explain. What we can't explain, the amount of variability that is not yet explainable, is what we're going to call error. And that reads sort of like an R squared. R squared is sums of squares of the model divided by sum of squares total. Okay. I guess, yeah, we'll go with that. So yeah, the what can't be explained is in error. Okay, so it's about 4:55. I think I'm happy to sort of like stop the sharing and then make sure I get the lab online. I redid it and I just didn't click the last little thing. So I gotta finish that, making the link for y'all. We're looking in the chat now. Oh, John's question. Cool. So what I'm gonna do is stop the share, and if you have any questions, we got a couple more minutes and I can answer those while I'm poking away at getting the lab turned on live.
Sorry, me again. So the alpha hats sum to zero, you said?
The alpha hats across the alpha hats sum to zero the way I want to think about them. Yes. That is only one of two possibilities, but that's the one, the way JMP works. That's what we like to do.
Okay, so it's not the alpha hats that are like the alpha hat number isn't what's describing a portion of the variance. What percentage of the variance?
Correct.
Okay.
If you take the alpha hats and square them and then sum that up, you'll see in the lab that that is tied to the what is explainable. And so, yeah, there is a tie in there, but not in an algebraically obvious or particularly important from the point of view of this class point of view.
So what exactly do the alpha hats show again?
Oh, it just says how different is this group than average.
So
Alpha
kind
hat.
of like the standard deviation of this group from the other groups.
Well, I'll just say it's the deviation of this group from the other groups. How far is this group above the other or others on average?
This is the deviation of this group from the mean of all groups.
Yeah, basically. Yeah, exactly.
And then square them, sum them up, and that should be percent of described data of variance.
Yeah, that equation's in the lab and you'll see it there.
Gotcha.
Okay, I'm going to turn off the recording so it processes quicker and I could get the video online sooner. But if one of you has a question before I do that, now's a great time to ask it.